to stop share. Sorry. We have to stop share.
I will first try to share the screen. Which apparently I still have to give permission to.
Oh, as you know.
No, I have to give permission here locally on my system.
Okay.
Do you see something now on the screen?
A presentation is.
All right, great. So the title you have already seen in the program. What I'm going to try to do is get you through a bit of some things we've done on the why and the how. This is absolutely not meant to be a linear, unidirectional presentation. So if you have any questions, remarks, experiences you want to share, please do so. Because I'm not sure if everybody is on the same level, because some people are studying specific sensors and maybe do not have an insight in the full story of monitoring of assets and health monitoring. I'll first also include a few theoretical things, but let's get into it. So first, on the why are we doing this? Because everybody has an idea. But in economy, things only work when the numbers match. And one of them is this. These are examples from 3 countries. So I don't want to point in any individual country, but it's about the Netherlands, Germany, and Italy, where there is, and it's in many more countries, the infrastructure we have today has reached a certain age. And in order to keep a country going, the infrastructure is needed. But the infrastructure needs to be good, it needs to be safe, and it needs to be able to carry all the weight. And what you see happening, as you see on the articles referenced, is that comes with a lot of investment needs. So we have a very strange situation where something is needed to keep the country running, but in many countries the money needed, it's not easy to find. So politically this is also a very interesting topic or subject. Second to that, there's also another issue. A lot of the infrastructure that you see is, or most or almost all infrastructure that you see is built by what you call contractors, civil contractors. So there are big companies that are having people, having big machines, and that really build the structures. An important background, the majority of the civil infrastructure that you use today is built based upon what you call a tendering process. So a public authority says, I need a bridge in this and this location. It roughly has to look like that. Then they go to the market and they actually invite potential construction companies to bid for that work. So people say, okay, I can do it for this amount of money. Another contractor says, I can do it for that amount of money. And in the majority of the cases, the situation is such that the cheapest bid wins. Which on the one hand, you could say, oh, it's interesting because, of course, as society, this is a way to save money. On the other hand, what you have is the situation has evolved such that the big compensation companies that are doing those things, they economically are running on a margin of 0.5, 1.5% of their revenue. And that economically is actually totally crazy. It is super unsafe, which means if anything goes wrong in any of those projects, that could mean, actually, and it has meant in the past few years, a bankruptcy of an entire company. And it's not even major mistakes. So there's a double issue. There's aging infrastructure, but there's also not all the public works today are still interesting for contractors because they are economically in a very difficult situation. And just to give you an indication, it's not all about technology. On the other hand, there's of course also good news. I might have shown this slide before. It's from a number of years ago, the story, but this is the Longfellow Bridge in Boston. So if you look at the bottom picture, on the one side of the bridge you will have MIT, the white dome. On the other hand, you have the city center. And a few years ago, that bridge was thoroughly renovated. Renovation actually, as you could, you see on the graph, that renovation costed $250 million. And when the renovation was in progress, one of the professors at MIT said, yeah, this is strange because it's hard for me now to bike across the bridge. This costs money. This is a lot of hindrance to the users. Is this the right way? And what he did as a result of that reflection is do a number of calculations. And he said, what would be an alternative? And one alternative would be, instead of building the bridge, letting it age, and fix it with a major overhaul years later, I maybe could do something else, or we maybe could do something else. And the approach he proposed was to build a structure and then continuously monitor and inspect and do small interventions every time it is needed. When you see a small degradation or a change that requires attention. And then he ran some models. And if you would do that same approach, if you would follow that approach, then actually at the moment where the bridge was finished, the restoration, the authority had spent $250 million. If they would have adopted a monitor, track, and fix approach since the beginning, on the same date, that bridge would have been at the same good condition, but only for $81 million. So that's just giving you an economical indication that there's still a lot of, despite the fact that today renovations cost a lot of money, despite the fact that there's a very harsh situation for a lot of the contractors, there's still a lot to be gained in the world of civil infrastructure. And this is some other literature about that context. So the table on the top right is from this paper. But there's also other elements playing. So if you look at the bottom left, and I'm going to see if I can do some pointer things here. Yeah, fancy. So there's a lot of replacement going on that costs a lot of money. Something else you could do is not even, avoid that a structure breaks or is damaged and you have to repair it. But you could also think at extending the life. And also that has a value because, of course, you do not have to build something new. You can still continue using the structure that you have. That has an ecological value, but it also has a financial value because that means that you can actually deter the investments on that structure. And here we're saying if we can increase the service life by 10%, some authorities can go into the billions of euros of savings. That's enormous if you look at countries' budgets. So just to give you a few numbers on the why and the relevance of all that follow-up and maybe of a lot of the things that you are doing now in your research life. We're not there yet. This is not fully implemented at all, but there is certainly a value if we can take better care of the infrastructure we have as a society. Any questions at this point, or remarks or contributions? Silence will be interpreted as a no. So why is it needed? So on the left you see an image of a recent collapse of a factory, a working building. I think it's a plant where they were making clothing. So why would you look at structural integrity of structures? There's many reasons. So there's the financial reasons I mentioned before. The top one is what we see on the left. These are things we want to avoid. Also, it can be that operational conditions are changing. So you want to keep on checking if the building or the structure is still fit for purpose. The extension of the design life, as said. So can we use it longer than it was initially intended? If things change, if you want to do an extension or use it differently, can it live with it? Can it survive that? The environment may change, loads, regulatory compliance, so also legal requirements may change or evolve, or you just have to check if you're compliant to certain rules. And then, optimizing the repair and maintenance efforts, that also on the general checking, what does it cost me to keep this building running? And one approach is actually not based on monitoring, it's based on doing measurements and inspections, and that is covered by an ISO norm. I've seen within the project also sometimes being referred to a number of instruments we'll be seeing later, but that's really a sort of a program that is set up where you have regular inspections. A lot of people involved, a very regulated process, and this is already very valuable because it gives you insights in the state of the structure, what's happening. We see deviations, yes and no, they can be interpreted, their severity can be assessed. And then here you see a lot of those instruments used there. This is examples mainly related to concrete-based structures, so you can look at the chemical state of the concrete. Is there chlorine getting in there? Is there carbonatation evolving? You can look at the mechanical strength of concrete, you can look at the state of rebars, etc., etc. You can really do testing of the materials. This is just another view on a lot of the testing equipment used. So this is all kind of like one-off inspections or test equipment that you go to the structure, you conduct a measurement or a campaign, you go back and you analyze what you have found or detected. This is another technology to see what's underground. This is also, and it is so important that within this project, there's even a specific PhD project aiming on that with Chandra. So if you look at a structure, you of course have to see how it behaves and what happens. But what is super important as well is that some of that behavior is related to actually the health status or the response to the usage. But a lot of what you see is also affected by external conditions, and those can be climatic things like temperatures, winds, but also traffic loads, etc., etc. So these are and are very important because those influences have a lot of effect on your interpretation and your assessment of the situation. Now, if you look at that monitoring and the assessment, where is it implemented? Actually, in a lot of structures. So, you have bridges, you have general seismic monitoring, you have dams, you have tunnels, pipeline systems, which I guess you've already had a little intro on specifically before, roads and rail, underwater structures, offshore structures, for example, oil and gas, also wind energy, wind turbines, nuclear power plants. So it's applied in multiple domains. And what you see in a monitoring system, this is the textual representation, but I'll switch to the graphical. So very typically, the layout of a long-term monitoring system is relatively similar. Here I'll give you a general overview. A bit later on, I'll give you a specific one on how we specifically approach it. But it all starts on the top left with different sensors located on the structure. The sensors, in this case, if you talk about continuous monitoring, they're continuously generating data, and you can have both wired and as well as wireless sensor. So that's what you can have. Then you have an acquisition hardware, which is sometimes embedded in the sensor, sometimes not. So it's collecting the data, transforming the analog system into a digital system, and then standardly you will have a communication hardware in order to send the data collected to a central location. Typically you could say storage and access location. Then your data is somewhere, it's collected, it is kept there, and then a lot of functions are required. Because of course the data needs to be analyzed. That's also a lot of stuff where you are personally involved in. Analysis, transforming the raw data into insights, into predictions, into state assessments. But standalone analysis on the data is not always enough. You also sometimes need data from external sources. These are, for example, meteorological stations, that can be traffic information. It can be information about the structure itself, like the design, materials used, etc., etc. And then what you need here is a user interface, because of course it's not only, the goal is not to monitor and to analyze, the goal is to do something with it. So you also need to interface with the end users, so that's also an important component. And very often also other systems are going to rely on your monitoring approach. Just as an illustration, imagine you have a high-speed train bridge and your monitoring system is monitoring the health of the bridge. From the moment you detect a situation of structural deficiency and actually the bridge should not be used anymore, you should have a direct connection with the train management system to avoid that more trains pass over, for example. So these are then outgoing connections where you can share alerts or insights with other users of your system or entities or people that could value or could benefit from your assessment of the situation. So that's the thing when it's running, but there's also an entire process preceding that, because some structures are identical, but if you look at civil engineering, a lot of them are not. And that means that actually to have a working monitoring system, there's a lot of stages you have to go through. And the first stage, now I'm depicting the ideal case. The ideal case is if you would be able to instrument a structure that is still to be built, and that you're also actually going to use the monitoring system through the entire design life. And then the first stage you have to do is engineering. Now, engineering is not only selecting how to monitor, what to monitor and where, but it's also selecting, you can actually optimize or change your design based on what you're going to monitor. If, for example, you're going to use a specific structural element that comes with some risks, or where not everybody is fully sure that it will withstand the operational life, or where it withstanding the operational life is a function of the conditions it is facing, you can design or devise a monitoring setup that actually helps you reduce those risks. So the engineering is not only engineering about your monitoring system, it is also matching the engineering of your structure with the engineering of your monitoring system to come to a more optimal and a safer situation in the end. Then the second is the sensor selection, because you know what data you need, what information do you need, so you're going to look for the most appropriate sensors. Also there, you have to balance things. On the one hand, you will say, yes, I need the appropriate sensor because it needs to be measuring with that resolution, that sample rate, etc., etc. But reality also means that there are limitations. Limitations on where you can place them, limitations on maintenance of those sensors themselves, limitations on how you can read them out, etc., etc. So the real world often is different from the academic world. So that's also something you have to balance between the ideal situation and real possibilities or realistic possibilities. Then next is manufacturing, and here manufacturing refers to the monitoring system itself, because then in practice what do? You actually collect all the hardware that you need. In the ideal case, you already assemble it on beforehand and you validate if it works. That is called a FAT or an FAT, a factory acceptance test, where you can already validate before all the stuff ends up on the structure that it is working. Because something you do not want, if you need to place a sensor on a difficult to access location, you need to rent a crane, put it there, and you only then verify if it's working, and it turns out that it's not working, maybe because of a faulty connection or whatever, you have to re-rent that crane and do the entire operation again. So you actually have to verify and test your monitoring setup entirely prior to installing anything. That's a very important element, because installation and works cost a lot of money. So that's the next phase. It's the installation, that is putting all the sensors, your acquisition devices, your communication units, etc. on the structure, install them. And then next is commissioning, the equivalent of pushing the play button. You start, but also at commissioning you will try and revalidate if everything works. some very typical examples, very practical lessons learned, but in the design phase, you say, I need this and this and this type of sensor here, that and that type of sensor there. And your system, in the very raw core, you will create a database with fields for every sensor. You will have a data stream. And you will, somewhere in the engineering process, you will set, okay, sensor ID 001 goes here, sensor ID 00C2 goes there. And you might assume, or you might think that the people or the crew installing the sensors executes everything exactly as you had planned it. Now, fun, in reality, that often is not the case. So what you also have to do during commissioning is test those sensors. For example, if you have accelerometer sensor on multiple locations, go by them one by one, hit them or solicit them in a specific way, and then in the data check if the order in which you solicited them is compliant with what you expect. Because if it is not, it might be that some wires have changed, sensors are on a different location, etc., etc. But that for every kind of sensor. So also that's what you would call a site acceptance test. You're going to validate if your sensors are still working and still alive, and if they all are on the locations that you want them to be, not only visually, but also in your system. Because it can be that the sensor with the code 002 is on the location of 002, but if somewhere along the route somebody switched to cables, the response will still end up somewhere else. And that such a situation is, again, creating you a lot of loss of time in the end, because very often you're going to start analyzing your data or doing treatment, etc. And only when something strange happens, you will start thinking, oh, what might be the reason? And you lose a lot of hours and manpower or woman power in analyzing those situations. So that's a lot you can avoid by just checking your installation prior to the full active life. Then, so the thing is commissioned, then the real world starts. There is a continuous data transfer, the storage of your data. So you need to make sure that your data transfer is continuously working. That's something you actively have to do during the entire process. Things may happen, like situations that we had. So we are already working for more than 10 years on monitoring. And last year we started having issues on our oldest installations. Why was that? You might be too young to remember, some of you, but before 4G there was 3G. And at some point in time, 3G was the top technology for data transfer. So we implemented in a number of situations a 3G router, which was then all it could do. What you see now is, since a bit more than a year, some of the telcos, they are phasing out the 3G network. So we first saw issues with the data transfer, and then for some locations there was none anymore. So it can be also related to cables, to everything, but also those simple practical things can happen. Your monitoring system might be working perfectly on the asset, but you're blind to it because your data transfer dropped, and not because of something you did, not of something you changed, but the environment you operate in changes. Data storage. That data storage on itself, terabytes of storage are not expensive, but it's a bit like what we've seen here in the project in a few instances. Data is only valuable it can be used. So data storage is not only storing it, it's also related to backups, but it's also related to having it in such way that people today, but also in the future, still understand what that data is. So storage also contains documentation, very important. And then you are running the process where you start adding value really to the data. So that's the process of interpretation, which can be, in the one extreme, manual. People analyze the data, write reports, make assessments, or on the other extreme, fully automated, where you have a number of algorithms continuously running and translating the data into parameters, into insights, into predictions, etc., etc. In the ideal case, if we look again at the situation where you have a continuous long-term monitoring and the system would say, dear owner, we see that there is an issue with the watertight layer in the section 5 and 7 of your bridge, send this PO to that supplier and contractor, and make sure that you put the bridge out of traffic between that and that day. That would be a fully automated approach. And then there's also an alarming system, which is, on the one hand, you need an alarming system, a bit like the situation I described before with the bridge that would be structurally deficient. But also an alarming system, it's a bit like with the data transfer. You have an alarming system, but you actually also continuously have to check if it's still working. Because an alarming system that is not working is as valuable as having no alarming system. And then there is reporting, because of course you regularly want to be a bit on the action, on knowing, okay, what is the state, a bit more of a deeper insight moment, and then the actions. If that's a bit what I told before, alarming is purely on, hey, something is going on, go and check or stop something. Actions is a bit of the translation I described before, like this is the works that need to be done on that location. So that's a bit of the full flow that you have when you look at the monitoring approach. So it's certainly, I certainly do not want to give the impression that the hardware is everything or that the software you have running is everything. You need an entire system to collect your data, but it also means work in preparation, work in execution. It's continuous attention required for a monitoring system. Any questions, remarks, suggestions, experiences at this point?
Yes, I have one doubt.
Yep.
For the reporting. So,
Yeah.
like for example, your client is like versus mobility, for example, here. So
Yes.
if you see some abnormal in your report, daily report, so what you do, like you go yourself or your team, or you just report to the client?
It depends, of course, on the contract that you have. If your contract ends with your responsibility being to mention them there is an issue, then that's what you do. If your contract also covers the other steps in the process, that's what you do. So that is rather a contractual / financial discussion than a technological situation. But on the other hand, of course, and that's a bit of a gray zone, if you feel that something is wrong, but you're not sure that it's entirely up on the sensors, maybe there's an issue with the sensor or anything else, if you're in an exploratory phase, it might be that you go there and do an additional check prior to sending out a full-fledged report and or a full-fledged alert, so to say. That's a bit of the gray zone when you're doing semi-experimental things.
Okay, so ultimately depends on the contract you have.
Yeah.
Yes, sir. Okay. Thank you.
Indeed. Super. Any other questions or situations you've encountered or you wonder about? And then I'll carry on. And this is a bit about the future. It's coming from a paper, so it's not something, the schemes I have not made myself, but also the monitoring approaches, they're also evolving a lot. So typically what you have is a centralized, very structured monitoring system. You have your sensors, you have your acquisition system, you have your unit where you do all the data treatment, and then it goes out. Things will evolve. First thing will be decentralized. So you will have maybe multiple monitoring systems working on the same setup. And there, of course, at some point they will have to come together because they need each other, or for interpretation, or because not one of them is fully covering everything. Which also can lead to the fact that maybe you're not having centralized computation anymore, but a lot of that is happening, as people like to call it, on the edge. So maybe on the monitoring devices themselves, and only the insights are distributed. And then the next one is even more advanced. It's when you start talking about smart structures, smart algorithms, agents, etc. At some point, it might be that the system itself detects a need for information, a need for data, a need for new algorithms, and might be able to request them or maybe devise for a number of those. So that's really far future, but a bit of more self-learning, self-aware systems. That's why I also put the image on the left. It is an evolution that you also start seeing more and more in the smartwatch world, where you have medical information being mixed into the situation, where it can make assessments on how to better behave as a person, or if something happens with your body readouts, maybe it's time to consult an expert, etc., etc. So that's really an evolution that is going on. Having a smart structure with a centralized system is certainly not the end point. There's a lot of evolutions that will take place. So there's also a lot of fun still ahead of us in this world of follow-up of structures. And then just a few examples, we'll go further, but some of the sensors that are used. So on the top right, this is a wireless sensor installed on a concrete wall, and it's a wireless sensor to measure the inclination. So if the wall stays straight, the sensor readout will always be the same, but if the wall would start tilting in any of the directions, the sensor is going to give a readout. This is a wireless sensor. You see it because of the antenna. This sensor is battery powered. What does it mean? It measures every half an hour or every hour, and the measurement interval actually influences how long you can use it before replacing the battery. Relatively straightforward. So this is on the outside of concrete. On the left, you see a sensor that you would actually put in concrete. So this is a strain gauge sensor that would be embedded in concrete. So it has to be installed prior to building the structure or during the construction process. That's a better way of putting it. And how is it measuring strain? Actually, those two plates, if the concrete would expand in the direction that I indicate here, the plates will move away from each other, so the sensor would grow longer, and the inverse for contraction. And then this is a wire that goes out, and this will go to a readout device. So on the outside, embedded in. Another example, this is an accelerometer sensor, so a vibration sensor that is placed on a structure. It's a high sensitivity accelerometer, also wired. Why is this interesting? In many cases you need vibrations in 3 dimensions, but not always the sensors are there that measure in 3 dimensions with sufficient sensitivity. So here, you cannot see it, but actually there's 3 sensors, and they are mounted on a cube, and the cube is mounted on the structure. And as such, you know that you're measuring in 3 perpendicular directions using 3 individual sensors. Also here, this is another illustration of why it is so important to do your checks, because it's not only the location, but also which of the channels is your X, your Y, and your Z. May sound very mundane, but very important to know that when you're doing it. And very often structures are very hard to access afterwards. Like this sensor is located inside a bridge where you need specific permission and time to get in there. So it's not because you're doing some analysis and you say, oh, I might want to check if the sensor is mounted right. It can be that you have to wait 6 months before you can go and check. So that's another reason why all those checks prior to or during the commissioning phase are so important. And this slide I added, it's also from an external reference, because it's interesting to see that you all talk about, or everybody talks about monitoring and adding sensors and doing continuous follow-up. But actually you can have multiple reasons or backgrounds for it. First, I'm gonna just look at RQ2 and RQ3. So one of your goals can be damage detection. I want to detect damage in order to either fix it or avoid it from happening again. That's more reactive. sometimes you might want to say, I'm actually, I want to see how it is deteriorating. Deteriorating is not necessarily damage, but okay, the structure is getting weaker, or maybe the concrete is starting to degrade without it being already an issue. But there your aim is a bit different, which means that also your tools that you use, both your sensors as well as your interpretation, is going to be different. It's not an or situation, very often it's an and, but the aim that you have will influence a lot of the selections you make. And then on the left one, so the yellow-orangey, why did I put it there? Because if you use the term monitoring, depending on the person you're talking to, they might be looking at different things. I think here in the project, a lot of monitoring is related to sensors being embedded or on the structure, and you're collecting data all the time. But for many people, doing regular visual checks is also monitoring, and that's correct. But also there, a lot of stuff is evolving. First wave was because of the drones becoming more low cost. So what you can do is take images, a lot of images, continuously. You can start treating those images, and as such, either automatically generate condition assessments or doing damage detection, damage assessment. Also, your situation is evolving a lot. Your drones are becoming bigger. They can take more payloads. You not only have flying drones, but you also have underwater drones that can look at underwater parts of the structure. You also have crawling drones. Interesting thing on those crawling drones is that, for example, they can start carrying the instruments that we showed roughly 12 slides back. The hitting test on concrete, they can do ultrasonic tests, they can do other tests. So what you could actually have is not a sensor permanently installed on a structure, but you might have a number of inspection systems continuously running on a structure, and as such also generating a sort of continuous data stream. So also there a lot of stuff is evolving. It might be that at some point maybe some of the sensors that you today install permanently on a structure, they might not be used anymore, but they are replaced by image analysis, automatic X-rays. I'm just naming a few things on that same structure. So there's a lot of stuff evolving there as well. Not only because it's partially because of algorithms on the image analysis, on data assessment, but also on technology, like how UAVs, autonomous equipment in any way, running inspections, and then also in the end you will get some reporting. Also there, more and more of it will become automated, etc., etc. So there's a lot of stuff evolving with the mobility of sensors, which is also opening up a lot of possibilities. Any remarks or questions at this point? All right. So first, I'll give a few examples from literature. After the break, we'll jump into reality. So this is a number of projects, and there you can see what have they been aiming at: detection, location, or quantification. So level 1 means it's, we might want to detect damages. Is there damage, yes or no? Level 2 is, okay, I also want to localize it. And then the most advanced level is damage quantification. But this is based on accelerometer data. So it's not based, the overview is not based on imaging or drone inspection. It's based on, and you will see, if you look at it based on accelerometer data, the higher the level, the more advanced your approach will be. And so there's a lot of stuff being done, a lot on bridges, on offshore platforms, and there you see the more difficult it is, the more challenging it is, the less examples you will have. And it's mostly made on natural frequencies, mode shapes, modal properties in any vibrations. And this is a bit of a tracking, where an overlap is. This is also from a literature source, where people deploy multiple sensors on a structure and do monitoring with 3 issues, or 3 things that they aim at. The right top here, it's early warning in case of disasters. So you see something coming. The examples they give here, unfortunately it happened, I don't recall if it was beginning of this year or somewhere last year. A bridge collapsed because of a ship hitting it. So your monitoring system can also be used to look at the environment. Is something dangerous approaching me? Is an imminent issue arising? The same for vibrations, maybe earthquakes. If you see them coming, for example, on a bridge or on a high riser, you might activate or change settings of a damping system such that your structure can survive the situation. So that's one thing. The same can be for a storm, like you see illustrated here. Then the second is on the bottom side, the green thing. That means, okay, something is happening now. There's an issue. A truss is vibrating too hard. We see cracks growing, etc., etc. These are things where you need to have fast response. Go and check, maybe ensure that you can still safely use it, etc., etc. And then the third part is the yellow part. That is where you are more at a long-term assessment. You see, okay, my structure is evolving like that. Maybe this way of using is not ideal anymore. So this is more related to lifetime extension and making repair cheaper, the B, or everything in the left upper corner. So again, an illustration of, it's all called monitoring, it's all using sensors, etc. But the why you do it can be totally different. And if the why is different, the approach you follow also is totally different. And then in an ideal case, if you are responsible for the structure, you want all of these elements to be there, because of course you want to know when something is coming up. You want to see when there's a defect, but you also want to have a long-term optimal usage and long life of your structure. And then some examples of projects just to give you an idea of how many sensors of what type are applied. So it's also from literature, the same work that we have here. This is all on bridges. So like here on the top, there you have almost 170 sensors. And this I see is it's a stadium where you have 200 sensors, but sometimes also the number is lower. Like here on this bridge, they devise a follow-up with a bit more than 50 sensors. While here, the Stonecutters Bridge, you will see an image later, there we're talking about more than 1,000 sensors on the structure. But of course, it's also a balance. This is what you will decide on in the engineering phase that I mentioned before. It depends on what you want, what you need. But if people say, okay, how many sensors do I need? Seldom you can give a quick answer on beforehand, because it really depends on your structure, on the risks you have identified, on your philosophy. Are you only aiming at one of those three elements? Are you aiming at two, or are you aiming at all three? That will also influence how many sensors you'll need. So it's an iterative process you go through. This is the example of that Stonecutter Bridge. So this is what has been instrumented there. It's also, as you can see, quite an interesting structure with two pylons, a lot of cables, quite a large span. And then, I'm not sure if you're all familiar, but what they have applied here, and I'm going to check. I will show a bit later. They also applied weight in motion systems. That's actually a system with which you can measure the weight of the actual traffic on the actual structure, which gives you a lot of insight in how to interpret the data or to correlate the data between behavior and response. This is a tower in China, Cannon Tower. Also here, if you look at the sensors, so we're also near the thousands. Also relevant, it's not only what sensors do you put there, sensitivity, but also sample rates. I'll show a few examples later on. But the phenomenon that you can monitor is a function of the sample rate. That's very clear. But also sample rate influences the amount of data you will generate. It will also influence, so the storage also affects where you can store the data. Is it possible in a database, yes or no? Do I have to go to files or any other options? So there's a lot of practical implications too on that sample rate. These are some indications on where they were located, the accelerometers. This is another distribution, like a bit like we've seen with the bridge, but I was looking, this is the schematic that they provided. And this is also interesting, you will see it later on, but more and more there's actually two fields. There's the in-construction monitoring and the in-service monitoring. In-service monitoring is continuously, but also very often you want to look at the structure while you're in construction. And that's for two reasons. Because on the one reason is, what is the structure doing with my environment and vice versa? It's also a lot to do with stakeholder management. Like if on a construction site, a lot of noise is generated, a lot of vibrations are generated. You don't want to create issues with the neighbors. So you want to check when am I making too much noise. You also do not want to damage structures around you. So that's what you are monitoring. You're actually monitoring the effect or the impact of the construction process on the surrounding environment. But if you're building a structure and, for example, you know you have challenging soil conditions, you also want to check, while the structure is growing and being built, is my soil still holding my structure, or do I see initial indications that my assessment of the soil condition is not what the reality gives? Or another thing, a lot of those structures are built out of concrete. Concrete has a curing time, so you need X days for the concrete to reach sufficient strength before you can start at the next floor or the next level. Since a few years, there is technology available that actually can give you in situ the degree of curing of your concrete. Sometimes you have to wait longer, but sometimes you can move faster, and faster means more efficient and means saving money. If you can start the 25th floor faster, you also can start the other floors faster, so your process or your project runs faster. So there's also more process related. And on the other hand, so it's process related, I can build faster potentially, but it also gives you afterwards a sort of a passport of the building, because it gives you an indication now, how did the concrete cure in that and that and that location, such that afterwards you have a sort of a proof like, see, we during the construction did everything as it was supposed to be, which is very important to know because of liability and also safety assessments. And here there's also some external systems like a GPS, but also visual inspection that is done continuously, and even the vision system can be used to monitor deflection or movement of the tower. In some areas, of course, earthquakes are happening, and there also you want to know what is the impact of the earthquake on my structure, and you want to know, is there any structural deficiency resulting from that earthquake? And these are the typical examples of data recorded. It's not what we didn't record it, it's also from the literature sources that we were cited before. But these are then, for example, strain levels and vibrations measured during an earthquake, that you then can compare to what you had modeled for the structure. Was this what we expected to happen? Yeah, this will also be in there. So these are the references used if you want. Any questions at this point from the audience? Or something you are missing?
Any question?
If not, I propose to take a 10-minute break, and then after this, we'll go into practical examples, practical illustrations, pictures, etc., etc. So, Yeah, this is a bit of a going from one to another. Maybe one item I would like to indicate, or two, are the two final ones. One thing that you also very often still hear is people say, okay, what is the sensor used to monitor this phenomenon? Or that you can only do one thing with one sensor, and that is totally not true. You will see some illustrations of it before, but actually with one sensor you can do a lot of things. If, for example, if you're looking at a vibration sensor, to take something relatively simple, you can use that sensor to identify and track natural frequencies, but you can also use that same sensor to identify if you're using it on a bridge, you can also use it to identify if a bridge was hit and how. So the same hardware, it's not always a connection, one hardware element, one problem. And then the last part is a bit related to what I illustrated in the engineering part of your monitoring setup. And in the sample rates, if you need some specific type of analysis to be done on the data, that imposes requirements on the data. Requirements on sample rate, requirements on resolution, etc., etc. And those are very important things. And sometimes, if your sample rate is too low, you cannot detect high frequency events, period. So it means you're blind for those things. So what you need, how you're going to analyze it, impacts what sensors you're going to use and how you're going to collect the data from them. So do not, because very often, people then, and then I mean general contractors, when you're going to put a monitoring system, on a bridge, they say, yeah, just tell me what sensors I have to install, and I will install them, and you will have the data, and you can do the monitoring. They will probably buy some sensors. You might give a brand and an indication, but if the acquisition system is the placement, if the way they read them out is not correct, then actually you also cannot do anything. This, what I said before, is a bit how we approach it. So we have everything in a platform, which is the red rectangle. So we put sensors on the structure that are continuously collecting the data. One thing that we do is also the data transfer is very flexible, because sometimes you have 4G, 5G access. Sometimes you don't have, you need a wired connection. Sometimes there's only a bit of data, then you can use a LoRa system. So that sometimes there's already a fixed network. So there's a lot of versatility potentially in your communication system. The sensors can be wired or wireless. The other information that is relevant, you also read it in. There you have to set up different types of connections. Those are industrial standards on data communication. But also the design is very important for the interpretation. Here we used the BIM, so the Building Information Management System, but that's also something you can, from that you can retrieve the geometry, you can retrieve materials, etc., etc. And then here is a system where we do all the analysis. We also use weather and traffic information. And what you have here on the right, so these are three vendors of systems. If you have, for example, a public authority that is working on highways, they will be sending people out to do things. And that is not manual anymore these days in many cases. Those are automatic systems. And it's a bit what is called also a ticket management system. So if somebody has to go and check if a railing on a bridge is still straight, or if the coating is to be visually checked on a certain part of the structure, somebody in the morning will need to receive the order to go and do that. And these are systems in which that sort of ticket management is done. So also there, when you detect something, in the end goal is that it's translated into a real action. And these are the things where, is the location where this is done with typically these type of softwares like Maximo and Ultimo. And the bottom part why do we put it like that? So you're going to do analysis. In our case, a lot of the analysis is done automatically, but sometimes you have to go and dig deeper. That's where you need experts. So that's where the analyst will interface with your system and your data. Sometimes it's simple things that have to be checked or repaired. That's where the technician interfaces. But sometimes also you need to know, okay, can we still use this bridge for 2 more years? then you need to interface with the manager. And why do I put this layer here? Because you cannot send the same type of information or the same type of report to those three people. An analyst needs a lot of data and a lot of context. A technician needs very focused information in simple wording, what needs to be done and how. And a manager needs very broad, simple information, and very often it's translated to a financial context. So you cannot just give those people a look at the raw data and have them interpret themselves. No, there's a lot of layers that need to be placed before those people can really do something with it in their specific job. And then in our case, we make some fancy dashboards which can be 3D on the structure. This is the architecture of the system. So our system internally, it's a cloud-based system. So we have everything running on the Amazon cloud, AWS, continuously, where we have functions that is data ingestion, data cleaning, data checking, storage in specific databases. So InfluxDB is a time series database where you can, time series of data can be stored very efficiently and also work with. If you look at context data, then you would more go to an SQL type of database. Then, of course, all the analysis is running in parallel with that. In our case, very often it's happening in Python, where you do stuff in the time domain and the frequency domain. And then here's the outgoing layer. So those alarms, reports, dashboards, but also output again to the information systems like BIM. And the ERP, which is then the enterprise resource planning, which is who goes and does what where. As said, first that, wired versus wireless. So this on the left is a wired sensor. On the right, it's a wireless sensor. So this is the top side actually of a water level sensor. So it's the top of a tube, there's a lid on it. It's a long hole that has been drilled by a machine. And in that, you have a pressure sensor with a membrane. There's a long wire going to the top. And this unit actually every so many times does a readout of the pressure and translates it into a water level. And then that data is transmitted wireless over a LoRa network to a central storage unit. Now it's time for you to work. Which are the advantages and disadvantages of a wireless system? I need at least 5.
Wires serve as like initiation sites for cracks. So being wireless means that you eliminate that variable. Secondly, the wired ones you need to exchange the wires as well, right? Whereas depending on whether or not the wireless one is passive or not.
Can you first go back to the dollar exchange? Can you explain that a bit more?
What? I couldn't hear you, sorry.
So first you refer to initiation of cracks, then you refer to exchange. But there I would like to understand a bit better what you want to say.
Well, basically, like if you have lots of wires, you need lots of multiplexers as well, right?
Yeah.
Whereas if you don't have wires, you don't need multiplexers, since you could potentially make it autonomous, right? A sensor node.
Yeah, yeah.
So yeah, that is also an advantage, less hardware perhaps.
Yeah. And you also mentioned the third element?
Yes, that was what is it? Data collection, right?
And data collection being an advantage or disadvantage, and of which system?
I guess data collection would be the advantage of the wired one, right? Since wireless. So it basically needs some external power to power it up, right? This wired one can just receive power from the main sensor node, right?
Okay, and then what would be technically the advantage for the user or for the system?
For the wired or the wireless, you mean?
Which you prefer?
Well, since my topic is wireless, I would say I prefer the wireless one.
Okay, thank you. Anyone else? Because we still need a few insights. Any other contributions? What are advantages, disadvantages of both that have not yet been mentioned?
I don't know if maybe you can ask some of the DC to take to answer. To give
Yeah,
you.
that's the
They
question.
don't move. I mean, ask one.
So if those that do not answer, for them, wireless and wired systems are totally equivalent and you can do the same and achieve the same result with them. Is that, can I take that as an answer from all those that have not responded?
It's a question you could have during your PhD defense. Huh? You have to train yourself.
They might do the same, but the wireless system has the advantage of showing less electronics, probably.
In what sense? Less electronics?
The cables, the wires.
Okay, yeah. And other elements? Because what are, if the advantage is less cables and wires, what are challenges or limitations or disadvantages?
Yeah, I don't know a lot about wireless systems, but to me, wireless connections can also be interrupted more easily sometimes, especially over distance. It also requires certain equipment that I'm not sure of. So it can be also a bit more challenging, I don't know.
Yeah, yeah. Anyone else who has potential disadvantages or issues in mind with the wireless solution?
I don't know about the wireless, but with the wired, I've seen like from the longer cables, we have some kind of less or some noisy signals, I would say. I mean, because of capacitance or resistance in the cable, with longer cable, we have seen the difference in the signal quality.
Okay. Yeah. Anyone else? Disadvantages of a wireless system? Maybe we have 5 in the meantime, but not a lot of elements. So one of the first I heard is about wireless as an advantage, because if you use wireless, you can avoid initiation of cracks. Yes and no, but it's an advantage because you have, and it's related to, you have less cables, so you have less passages you have to make, etc. But also, there's other methods also to avoid cracks. So I would at this point not use wireless as an argument, or crack initiation as an argument to choose between wired or wireless. The big disadvantage of the wired solution is indeed all the cables you need to have. It's on the one hand, it's a cost, copper per meter, but also it's a lot of work. It means hours of work during the installation process. You have to route them, you have to check, etc., etc. That's absolutely a disadvantage. Also can become complex. But on the other hand, you also sometimes need it because you sometimes need continuous data. And one of the disadvantages of the wireless solutions, so they are battery powered, which means that they are limited Not, and just to be sure, so the limitation on wireless sensors and their battery is mainly related to transfer of data. So on a wireless sensor, it is actually the data transfer that takes the most energy. It's opening the connection, sending the data, collecting it again. For many techniques, collecting the data locally on the node. So this thing here is called very often a node, and then it's sending it to a gateway, which is receiving the data. So the most energy consumption here is on the sending of the data. And what you then also practically see in reality is that sometimes, due to whatever reason, the nodes are finding it more difficult to communicate, or you have a sort of a Faraday cage effect playing, etc. And then you see the battery depleting very rapidly, much faster than you initially anticipated. That's also an issue there. Then you have to go and replace the battery. So on the one hand, if you have an issue with a cabled sensor, you have to reroute part of the cable. That's also expensive and difficult. But in the ideal case, it never happens because your sensor is well protected, etc. If you have a wireless sensor and you're looking at long-term monitoring, you will have to go in and replace batteries. And that's also the cost of that is the battery, which is not massive, but it's also all the associated work. Going there, replacing it, the hourly costs, managing it, etc., etc. So that's also something you have to balance in the entire story. Also, and that's why I put the picture on the right here, it's a relatively new technology, the wireless sensors, but you almost all the time need an antenna. And with these sensors, for example, we had a lot of issues with water. Although they were indicated as being IP65, very high protection degree, a lot of those sensors, there was water coming into the node. And then the node went out and your battery is done. So you have to start replacing those nodes. So certainly today, always be careful. We actually ended up tweaking the sensors themselves, so the nodes, and we started filling those here with the hydrophobic substance to avoid that water would get in there. Very practical stuff, but it can, if you're in a commercial situation, that can make or break your project. Because if you have to go and replace all those nodes, it costs you money because of the hardware, but it also costs you money because you have to go there. And very often, like this was on an airport, you need to get the permission to go there. So it's not a trivial choice, selecting between a wired and a wireless solution. Any other observations or insights after this?
I have a question about wireless sensors. Is it?
And then I'll go further. Go ahead.
Yeah, with wireless sensors, can we embed them in deeper depths? Like how far can we embed them? How deep would they still work?
Yeah, so there's, of course, if you embed your sensor, wireless sensors, the deeper you go in the structure, in the soil, etc., the more the signal will be attenuated. So technically, you might be able to go deeper, but your signal will be reduced in strength, which means it will have to communicate more and it will lose battery power more. So what you typically would do is the example that you see here, the circular object you have here is the lid of a tube. That tube is 20 meters long. So the sensor is 19 meters below the soil level, but the transmission, so the wireless part, is here at the top level. So that could be a solution.
Mm-hmm.
But if this node would have been 19 meters underground, most probably it would deplete its battery every so many days.
Okay.
So that's something you have to balance.
Thank you.
Other practical questions or remarks? Then I'll jump to a structure. So this is one of the structures that we've been following up. So it's actually my hometown. where I lived till I was 20. So this is a bridge that was built in 1935, a bit before I was born. And it's a train line connecting the city of Brussels and Antwerp, and it's somewhere in the middle. And yeah, this has now become a sort of a monument, because it's called a Vierendeelbrug. Vierendeel is an architect who devised this type of bridge. This is used a lot, and yeah, the owner wants to prolong the operational life of the bridge. It's a steel structure. This is the bigger view of the structure. And this one we have instrumented with a lot of sensor types. The goal was to see how is it doing, and structurally, how healthy is it still, and how does it evolve as a function of time. I'll go back here. So one of a number of the things that we did. So for a bridge, what you typically have, or what you often have, is that one part of the bridge is fixed to the land on the abutment, and on the other end of the bridge, at the other side, so here on the right, you have to allow it for some free movement, because typically under loading, but certainly under temperature, a bridge will expand and contract. If you, in many cases, would fix the bridge at both outer ends, yeah, it will generate a lot of internal forces which can create cracks, etc. So what you need is typically, like on one side, is what is called a bearing, allowing the bridge to move horizontally. On this bridge, the bearing was designed in 1935, so it's an older concept. But we still want to know, is that bearing working? And what you see here is actually a displacement sensor that we have installed to monitor the horizontal displacement where the bearings are located. So the thing that you see here is the concrete, it's the land side, and then on a bit higher here you will have the bearing. Another thing you want to know is, okay, how is this bridge, what they actually wanted to know, or what many people that have a bridge want to know, is what is the vertical deflection in the center of the bridge, which is a deformation as a function of time. And you could say, I could put a laser sensor here that is continuously measuring the distance between the soil and the bridge. But problem one, there's trains riding under the bridge. There's a lot of dust. There's a lot of high voltage electricity here because of the train, so you cannot do whatever you want. And on the next to the rails, there's a lot of work, so they're continuously changing the situation with people that are unaware of the situation that is above. So what we said is, we will not do a direct measurement of the distance between the bridge deck and the soil. We will do an indirect measurement by installing a number of high-resolution inclination sensors. Because the bridge, it will not, if it fully goes down, that's something different than when it bends and it becomes a bow. And so if you have a number of inclination sensors, you can actually calculate the full bending. And if you can calculate the full bending, you can also determine, okay, how much was the vertical deflection. And this is then one of those sensors that we installed, an inclination sensor. So this is one of the codes that we use, for example, to identify the sensors. Another interesting element here, these are magnets, because we do not want to create or generate stress concentration points. We do not want to be drilling in the bridge structure. So a lot of the sensors that we install are installed using magnets. Long-term, very strong magnets, and you do not have to drill. It also accelerates the installation process, and you're not affecting the main structure. And this is some of the results. So we measure the deformation horizontally, so the bridge contracting and extending. But measure how much weight is there on the bridge. We decided also to measure with high resolution the vertical displacement at the bearing. Because if there's a heavy train on the bridge, the bearing will be partially compressed, and that compression is proportional to the weight. And what we did with that, we can then, the continuous data stream, you can identify a passage because it's a peak in that compression. But by tracking the amplitude of the compression, you also have an indication how heavy was that train. And that's what we put here. And what is interesting to say, this is so the red trains are the heavy ones, the yellow ones are the medium, and the green are the light ones. This tail here on the right means there's a lot of what you call work traffic, like single trains passing by. And what is cool to see, this was actually the date. We're following up this bridge for since a while. This was during the COVID period, and this is one when one of the measures ended, and you saw that the trains were getting more heavy because there was more people sitting in the trains. So there was an increase in the number of heavy passages and a decrease in the number of light passages. Why is this important? On the one hand, it's interesting to see that, but your bridge has been designed on, okay, how many passages of what type will we see, which will influence fatigue of the structure. And you start that based on an assumption, but in reality things will change. This bridge is there since 1935. I think that steam engines have driven over it and other types as well, all with different weights, trains have become longer, etc. So actually what you need to do is continuously update your lifetime expectation based on the real loads taking place. And this is what, so you start from a displacement sensor, but you're actually building up data to assess, okay, what is the remaining life in this structure? This is the raw data, the vertical displacement. So those are two sensors, the yellow one and the blue one is the sensor. This is the real data. And you see an evolution. You see a kink here. The gray curve is the temperature. So that's expansion, compression as a result of the temperature. And then you see spikes. Now those spikes, those are the passages. So what we look at is, for example, okay, what's now the amplitude of this jump as a function of the temperature? And that, if this would be linear, you have a fully normal elastic behavior of the bearing, but that's not the case. You see there's a little bending there. And you also see that the response of the two bearings is different. Because of the age, the two bearings are different, and they also do not have an elastic response anymore. Very interesting to know. Also, if those bearings are not exactly acting the same left and right, the bridge is actually going to bend. Because if one bearing is giving more resistance than the other one, the bridge cannot just expand and contract, it will actually move a bit. It will start bending a bit, creating internal forces, creating potentially internal stress concentrations that you do not like. While here, so on the left side, we isolate every individual event automatically and we create those curves. What we also do is the inverse. We filter out all the individual events and we only look at displacement. And this is then the displacement of the left bearing compared to the right one. The left image here is the horizontal displacement. This is the vertical displacement. And you see here, this is very linear, so this means horizontal displacement is going very well. The two bearings are acting the same. On the right, you see the vertical displacement, and you see here a number of points there. What we now know is actually something has changed in one of the bearings in time. So something must have broken internally, because normally this should also be a perfectly linear curve. So the point in time where these points started to appear, we know that something was broken in the bearing. And that's a moment where you can either trigger a visual inspection, and if that turns out to be bad, you might even want to start a replacement or a fixing process on your bearing. So it's one data stream, but by filtering out events, by looking at thermal information, you can actually derive a lot of stuff from that one data stream. You're also looking at the natural frequencies. Here is funny because we were able to derive the natural, or to identify the natural frequencies both from the accelerations, there's also accelerometers on that bridge, but also from the strain data. So we could get the natural frequencies out of the strain, so we could generate very nicely spectra out of the strain. What we used here are classical foil strain gauges, so no optical ones, foil strain gauges. And we have strain gauges on the vertical parts, bending and tensile. We have strain gauges on the arcs, and we have strain gauges on the bottom part. And the vertical lines, so the client, they made a finite element model of the structure. From that, they derived where theoretically the natural frequencies would be located, and that we could match. And we see that very often we are very near, what we measure is very near to the model. So that's already positive. It means that there's not A, that the model is good, and B, that there's also no major structural issues with this bridge. So, but this is these are then the frequencies that you would be continuously following up in the monitoring here. And as I said, so with a very interesting point, we can actually track them too from the strain data, which is very cool. And then something we do as well, because you can look at phenomena, but actually what you want to do is what's the actual aging of the bridge. What we also do is actually calculating what is the true rainflow counting, like, okay, what are the actual stress cycles that this bridge went through, which looks, okay, how is now today in reality the damage accumulating in the bridge, but you can also identify sometimes, okay, when did we see a jump, or in other structures we see an inflection, that the speed of damage accumulation, accelerates or slows down. Which also you can match then with changes, maybe traffic changed, maybe there were works around the structure, and then as such you can get into an insight, okay, what are things that are good or positive for the bridge and which are things that are bad or negative regarding the long-term life. Any questions or remarks on this one? If not, I'll show a few more
so there
examples.
is Yves. So I would have a question, but about temperature, but I will not ask it. But we have 15 minutes left before the start of the presentation of Mario's. So if you could, as we started late, unfortunately, maybe if you could stop 5 minutes before 11, so that we have a 5-minute break. Okay, thank you.
Yeah, we'll do. No problem. So now we go to a fully concrete structure. This is a lock somewhere in the Netherlands, and it's not a lock to equalize a water level to let ships pass on a river, but this is or on a canal. But this is a lock that is used to shield off the land when the water level is getting too high. Focus here is on the concrete. Why monitoring? Because the contractor here, together with the owner, the authority, they wanted to use a number of alternative types of concrete. Concrete with a different composition because of it having a lower CO2 impact, and also concrete containing part recycled material. And they wanted to see, is this concrete performing as well as normal concrete or better or worse? And that's, we're talking about these structures here, so the tower and the sides. And what we did was then embed a number of sensors in there. So the bottom one is a typical reference electrode. So with that, you're gonna check if the potential, electrochemical potential of your rebars, how that is evolving. If that changes in a certain direction, you might have corrosion there. This is an ER sensor, electrical resistance. Here we can measure actually the material loss on this element. So if there would be corrosion inside, we can even monitor how much it is. And this sensor was pre-embedded in concrete, but it's actually a electrical conductivity sensor. So we can monitor continuously the electrical conductivity of the concrete, which gives an indication when there is water ingress, but also when there would be chlorine and or so these are the sensors when they were embedded during the prefab process. These are the same sensors on a different location. And this is then the reality, the readout. So all sensors are wired to an acquisition unit. And then on top of the structure, you have here an antenna, because we're also here using the 4G network. So that is what the practical system looks like in reality, a clean install. And then some of the data on the material loss. This is roughly the same, so that I will skip. Interesting one is this, because of course structures degrade because of loads, which can be mechanical, etc. But you see here a situation where there's a higher piece of land, there's a train track on top of it, and what you can have in that case are stray currents. So the current of the train is getting the current from the catenaries, from the top, and is then actually normally re-injecting them into the rails, and they can travel back to the substation. But sometimes the currents go elsewhere, that are called stray currents. And here you see anchors being used to stabilize the soil. Now, if those stray currents go wrongly, they can actually get into those anchors and out and make them corrode, which would actually weaken the soil here. So that's why we devised we actually installed a number of sensors in and around those ground anchors. This is the installation process. Then we have an acquisition unit there, continuously monitoring. This is after the installation, so this is the unit, all the cables going through a protective tube. This is what it looked like a few months later. Nothing is seen anymore. But the cool thing is that we can then generate, for example, these kinds of curves. So we check, okay, what is the material loss? But we also had different potential measurement points in the body, and we can actually continuously visualize the potential field in the soil. So we can really see where the currents are going. So this is not monitoring structural things. This is actually monitoring electrical fields, electromagnetic fields that might influence your structure internally, corrosion related. Then I'm gonna skip maybe some things related to lifetime extension. This is something we did on a bridge in Germany. So this is the Fehmarnsund. That's where Germany and Denmark are close at the east side of the land connection. This is an old bridge with cables, but you see that the cables cross. And this is an image on the crossing of the cables. Now, before we went there, the cables were actually clamped together with two rectangular plates. And what was the result? Some of the cables got damaged because of friction between both. And then the bridge also has now reached a monumental state, so they want to use it longer. And they have actually devised a new concept where you have a tubular protection and some rubber elements in between. And we have instrumented some of those actually to monitor how are the cables moving under wind loading conditions. It's with bolted connections, so we monitor also continuously the bolt tension or the bolts holding, etc. And as such, we could validate if this new concept is working, yes or no. So this was a temporary setup, a number of months. But as you can already see, installation here is also very challenging because you need a high-level cherry picker. You can only go there when wind conditions are okay, etc., etc. So this is interesting but challenging. Here you see displacement sensors with which you measure, okay, how are the cables moving? This is also related to lifetime extension. It's a chimney on an industrial lot, and where you can see there is a crack. So here we do continuous follow-up of the crack. How does it evolve as a function of time with a wireless system? So here is a gateway that collects all the wireless data. This is in a building under construction with very challenging conditions. It's a building that is partially above a metro, but it cannot rest on the metro tunnel. So it has a very specific anchoring system. And here we installed in the basement a sort of a water leveling system, which we can track very precisely, is there any vertical movement? So it's a tube filled with water, and it has multiple points where it surfaces, and we continuously measure the level of the top of the water surface. What people did for ages when they were building and wanted to see so it's the Archimedes effect that you're now doing automatically and continuously. And I just want to introduce this one as well, because loads can be very different. This is where we actually have the interface between users and owners of infrastructure. So this is a tram, this is a switch of a tram, and a contractor is responsible for the health of the switch, but the trams are managed by the public transport company. But if the public transport company doesn't maintain the trams well, if the wheels are not round, if the wheels are deformed, or if the axles are bent, they generate a lot of hits on the structure. And as such, the rails, but certainly also the switches, will deteriorate. So what we monitor here is actually the dynamic behavior, the impact of the trams on the switch, such that the contractor can actually warn the public transport company, like, hey guys, you're damaging our machines, our assets. So it's also preventive, because when it has to be replaced, it's at the cost of the contractor. But of course, if your client is damaging the structure, you also want to know. So this is also an application of a monitoring. It's just like, okay, what are people doing with my infrastructure? And is it degradation because of natural or normal processes, or is it because of bad usage? And this is then the system that we have behind for actually the more red it is, the higher the impact of the tram on that switch. So the red, those are the bad ones. Those 2 trams are bad trams. Then maybe a final one. This is a structure, it's a recent bridge over the ring road around Brussels. The big challenge here is that it's made out of weathering steel, which for Belgium is something new in civil infrastructure. So we were asked to devise a monitoring system for that. So that's what you see here, the bridge from the bottom. So also here we installed deformation sensors. So this is a bearing, a modern bearing, so it's a rubber block. So it allows movement in all directions, up, down, left, right, front, back. So if it's heating up, the bridge can move. So we monitor the vertical displacement and the horizontal one. Under here you see strain gauges. So we monitor the deformation of the strain at certain stress concentration points, the temperature for reference. Inclination again, so to look at the high level deformation. These are the accelerometers, high sensitivity. But we also put sensors in the concrete. This is a gutter, during the construction, a gutter where the water will be evacuated. Also there it was tracked. A zoom on the conductivity ladder. And then also corrosion by electrical resistance, where we will monitor, okay, what's the loss of steel as a function of time, and is this, will this be going as we expected? Yes or no? Any questions, remarks, suggestions at this point? If not, I will terminate so that you can.
Okay, so I have a curiosity question. You have in one of your application embedded sensors measuring the apparent resistivity, or is it something that you have developed, or is it something classical? Or?
Yeah, it's something we developed. So we have a system where we can apply a current and record a voltage response in AC, and then we can correlate that with physical behavior in the material.
Okay. Okay. So I will maybe connect. If you can send some information about this, I can connect with people in our universities that are working in resistivity measurements and electromagnetic measurements. They would be interested.
Okay. Yeah. Sure.
Thank you.
Any other famous last words?
Okay, so not many questions. So I have to thank you again, Yves, for your presentation with a lot of use case where we see the complexity and the challenges that have to be faced. So now we are designing new sensors. I don't know how long it takes to go from an idea to something that is used on site, but I guess maybe some of the work we are currently doing in this project will go on site one day.
Yeah, absolutely.
So thank you very much again. So for the doctoral candidate, I'd like to start DC presentation on time. So it's in 3 minutes. So it's a